Hello, everyone. Let's begin with an interesting thought. Have you ever noticed how people are seated in a class according to a roll number list? That's exactly how elements are arranged in the periodic table, following their atomic number and electronic configuration. Each element in a period has the same number of electron shells, while elements in the same group share the same number of valence electrons. For example, hydrogen with one valence electron sits in group 1, carbon with four valence electrons sits in group 14, while nitrogen, oxygen, sulfur, and chlorine all take their rightful places in groups 15, 16, and 17. Their positions immediately hint at their chemical reactivity and bonding patterns. Now let's explore how valence electrons determine an element's group. Hydrogen, atomic number 1, has one valence electron and can be placed in group 1 or 17 depending on context. Carbon, with atomic number 6 and 4 valence electrons, goes into group 14. Nitrogen has 5 valence electrons, so it belongs to group 15. Oxygen and sulfur both have 6 valence electrons, placing them in group 16, and chlorine with 7 valence electrons settles into group 17. A quick glance shows that the periodic table is nothing but a systematic reflection of outer electron configuration. One fascinating group property is allotropy, where a single element can exist in more than one physical form. Think of carbon, sometimes it shines as a diamond, other times it is a dull, soft graphite used in pencils. Oxygen also shows allotropy, existing as O2, which we breathe, and ozone, O3, which shields us from harmful UV radiation. Groups 14, 15, and 16 particularly showcase this phenomenon, and it beautifully demonstrates how different atomic arrangements of the same element can give rise to very different properties. Another crucial property is electronegativity, the ability of an atom to pull bonding electrons towards itself. Nonmetals like nitrogen, oxygen, and chlorine are highly electronegative, meaning they strongly attract electrons. Metals, on the other hand, lose electrons easily and are therefore electropositive. Across a period from left to right, electronegativity increases, while down a group it decreases. That's why fluorine is the most electronegative element in the entire table, while cesium and francium at the bottom left are the least. This trend explains why sodium and chlorine form an ionic bond in sodium chloride, while hydrogen and chlorine form a covalent bond in HCl gas. As we move from left to right in a period, the nonmetallic character of elements increases while metallic character decreases. Nonmetals tend to gain electrons and form anions, whereas metals lose electrons to form cations. For example, chlorine, a nonmetal with strong electronegativity, is highly reactive, while lead, sitting further down, behaves as a typical metal. These trends in metallic and nonmetallic nature are directly connected to ionization energy and electronegativity, and they are among the most tested ideas in board examinations. Let's solve a classic example. Arrange carbon, nitrogen, oxygen, and fluorine in decreasing order of electronegativity. Across period 2, electronegativity steadily increases. So the correct order is carbon less than nitrogen, less than oxygen, less than fluorine. That makes fluorine the most electronegative element overall, explaining why it acts as the strongest oxidizing agent among halogens. Remember this order C, N, O, F because it not only helps in exams but also in understanding bonding behavior in organic and inorganic chemistry. So, to wrap up, the placement of elements in the periodic table is entirely based on their valence electrons and shells. Groups are determined by the number of valence electrons and periods by the number of electron shells. Unique properties such as allotropy, electronegativity, and nonmetallic character follow clear and predictable patterns. The periodic law allows us to forecast the chemical behavior of elements simply by knowing their position. That's the beauty of the periodic table. It is not just a chart, but a powerful predictive tool for chemistry. I hope this session helped you connect these periodic trends with real world chemical behavior. Until next time, remember, the periodic table is your roadmap to mastering chemistry.